So I think we'll not wait for now. So, Dr. Saurabh, I'll take half a minute for your introduction and then you can start.
Okay.
Dear students, we have with us Dr. Saurabh Srivastava, who is Chief Scientific Officer at vidcare Innovations Private Limited, Pune, and he has over 14 years of research experience in the area of microfluidics, immunoassay development, and BIIS also working with notable research groups both in India and Europe. He has done his master's in nanotechnology from TU Delft at Netherlands and another master in molecular bioengineering from TU Dresden, Germany. His PhD is from Wageningen University, the Netherlands, on biosensors-based detection of tuberculosis biomarkers. On behalf of Srishti, I welcome you, sir, and we are very happy to see you again in this workshop. Over to you.
Thank you, Dr. Mega, for your kind introduction. So, today the topic that we'll cover is chromatography, and more specifically, it's gas chromatography, its principle, working, and applications. So, yeah, chromatography comes from two words, that is chroma, which means color, and graphing, which means to write. So, chromatography as a whole means color writing. The technique was first carried out by a Russian botanist. His name was Mikhail Swat, and what he did was that he eluted a petroleum ether plant extract on a column which was filled with a stationary phase calcium carbonate. Uh, is it audible, right?
Yes, yes.
So, in the liquid phase that he used was liquid hydroxy carbon, and what he did, he separated three components from it. One was xanthophyll, which was yellow in color, carotenoid, that was orange in color, and chlorophyll, that was green in color. So, this is basically how chromatography, in principle, started. Now, uh, what exactly this chromatography is, if we talk in terms of definition. So chromatography is a technique for separating mixtures into their components to analyze, identify, purify, and or to quantify the mixtures of the component. Now, the component to be separated are distributed between two phases, that is the mobile phase and the stationary phase. Mobile as in because it moves, that's why it is called as mobile phase, and the stationary phase is the phase which is stationary and which causes the separation, is and hence it is called as stationary phase. Now, suppose you have a sample which is made with different components, and you want to isolate or extract these components separately from it, then you will use chromatography. Now, before we move on further, let's see some basic terminology that will be used during this lecture and which are there. So, mobile phase, as I said, a solvent that flows through the supporting medium or through the stationary phase is called as the mobile phase. Now, this mobile phase is the phase that is responsible for taking your sample along, which needs to be separated. Sample here means the mixture or the um, uh, component that you want to separate. Then comes stationary phase. Stationary phase is a layer or a coating on the supporting medium that interacts with the analyte. So the mobile phase passes through this stationary phase, and the component molecule that you want to separate interacts with the stationary phase, and thus their separation is caused. Now, supporting medium is basically a solid surface on which the stationary phase is bound or coated or is filled. So it could be a tube, it could be a plate, it could be a surface, and so on. Now, there is one more thing, that is retention time. So, retention time is the time for which your component was retained into the column or was bound to the stationary phase. So, depending upon this retention time, you identify the component that you were trying to separate. Okay. Now, if we talk about the principle of chromatography, so column chromatography or chromatography as a whole is a physical method of separation that distributes the component to be separated between two phases in a definite direction. So it will separate the components in the direction of movement from either bigger in size to smaller in size, or higher boiling point to lower boiling point. So these are few things, or based on affinity and based on binding, it separates the column in the direction of the movement of the mobile phase. Now, substances are separated based on their differential distribution between two phases. Another thing is, substance will move with the mobile phase at different rate depending upon their partition or distribution coefficient. So, how their distribution coefficient or how their binding is or affinity is, it will get separated in the direction of the flow of the liquid phase. Now, based on uh, stationary phase or mobile phase, or the principal, chromatography can be classified in three different ways. So first is based on the mechanism of separation. In this, it can be uh, divided into four types. So the first type is adsorption chromatography. So in absorption chromatography, uh, it works on the principle of adsorption. Here, the analyte molecule are adsorbed on the resin. Resin is the stationary phase that is used in this case. Like, for example, affinity chromatography or high performance liquid chromatography. Then, partition chromatography. In partition chromatography, the separation is on the basis of sample partition due to its solubility in liquid mobile phase. So, there are some samples which are easily soluble in liquid, some samples will be there which are less soluble in liquid. So, depending upon their solubility with the liquid mobile phase, partition chromatography works. Then the third one is ion exchange chromatography. So, in ion exchange chromatography, there is an exchange of ions. That is, ions are attached with the resin. Resin is the stationary phase here, and the ions in the sample or analyte to be isolated replaces these ions from the resin and attaches itself to it. So basically, this is kind of a replacement. The resins are pre-attached with ions, and what happens when your component that has to be isolated comes into the column, it replaces the existing ions on the resin with itself, and hence they get stuck into the column. So this is ion exchange chromatography. Now, fourth one is size exclusion chromatography. So in size exclusion chromatography, the separation is based on the size of the component to be isolated. This is also called as gel permeable chromatography, as it uses uh, as it is used when you have to separate or isolate conjugates from the mixture. Then similarly, the other classification is based on mobile phase. So mobile phase can be liquid, gas, or supercritical fluid. A mobile phase, solid mobile phase is not possible uh, because of course it's solid and it will not move. So a solid mobile phase is not possible. Now, in liquid chromatography, the mobile phase that is used is liquid. For example, normal chromatography or reverse phase chromatography, then hydrophobic or hydrophilic interaction chromatography or ion exchange chromatography, FPLC, or FPLC is fast protein liquid chromatography or affinity chromatography. In all of these chromatographies, The mobile phase that is used is liquid chromatography. Then the second one is gas chromatography. So in gas chromatography, the mobile phase that is used is gas. And here the example is GC, gas chromatography. Then the third one is supercritical fluid chromatography. So in supercritical fluid, mobile phase is a supercritical fluid. That is, supercritical fluid is a substance which above its critical temperature and pressure is a supercritical fluid, is a fluid. Hence, in this case, no distinct liquid or gaseous phase exists. So basically, uh, at a specific temperature and pressure, it will be a liquid. So that is a supercritical fluid. And example for it will be carbon dioxide. Now, this type of classification for chromatography would be based on the shape of the chromatographic bed. So it could be planar or column. So this chromatographic bed is the place where the resins are present or immobilized. Now in planar chromatography, the resins or the separation bed where the separation has to take place is on a planar substrate. Example, paper chromatography, where liquid molecules are dried on a planar surface, and TLC, where silica gel is dried on a glass or aluminium surface. The second one is column chromatography. So in column chromatography, the stationary phase is basically packed or filled in a column. For example, ion exchange chromatography, then high performance liquid chromatography, hydrophilic or hydrophobic interaction chromatography, affinity chromatography, and so on. So column chromatography can further be divided into two types. One is packed column chromatography and the other one is tubular column chromatography. So packed column chromatography is when the column is packed, like in HPLC or affinity chromatography, while in tubular column chromatography, there is a tube-like structure or which is coiled or non-coiled columns. And example for where it is used is gas chromatography. So in gas chromatography, we have a column-like structure that is used as a um, m- chromatographic bed to have the gel, separating gel. Now, what are the different types of chromatography? So we have normal phase chromatography, then we have reverse phase. So normal phase chromatography, the stationary phase used is polar, while the mobile phase that is used is non-polar. So this is the, let's say, the basic or the main classification. So in normal phase chromatography, a stationary phase is polar that is used, while in mobile phase is a non-polar solvent. Then in reverse phase is basically the reverse of normal phase. And what happens here is stationary phase is non-polar while the mobile phase is polar. Then hydrophobic interaction chromatography, here the separation is on the basis of hydrophobic interaction between the stationary phase and the sample to be isolated. Then hydrophilic interaction is based on hydrophilic interactions. Hydrophobic is basically water heating. Hydro is water and phobic is heating. So hydrophobic is water heating. Similarly, hydrophilic is hydro is water and philic is loving. So basically water loving. So here the separation is based on the hydrophilicity of the component that has to be separated. Then ion exchange, as I said earlier, ion exchange is basically separation on the basis of ion and how these ions are binding to the matrix. Matrix here is the stationary phase. Then fast protein liquid chromatography. Here you isolate protein molecules on a liquid chromatography column where you have stationary phase filled, and the interaction of proteins with the stationary phase causes the separation. Then size exclusion chromatography is separation depending on the size of the component that has to be isolated. Affinity chromatography is based on the affinity of the component to be isolated with the stationary phase. Supercritical fluid is again how how your sample is interacting with the supercritical fluid. It depends on size as well as of other physical parameters. Then gas chromatography is basically isolation on the basis of firstly the boiling point, secondly the size of the molecule. So this we'll discuss further in the slide. Then next is your paper chromatography. So it's paper chromatography and thin layer chromatography are basically examples of planar surface, and here the separation is on the basis of size and so on. So now moving on to gas chromatography. So as the name suggests, mobile phase that is used in gas chromatography is gas, while the stationary phase that may be used in the gas chromatography can either be solid or can be liquid. If we are using a solid stationary phase, then the gas chromatography is known as gas solid chromatography, or GSC. And the principle behind this GSC, or gas solid chromatography, is adsorption phenomena. Then the second one that we have here is when we have a liquid mobile phase. So here it is called as gas liquid chromatography, or GLC, and it is based on, the separation is based on partition coefficient phenomena. Now, the theory of gas chromatography is dependent on Van Demeter equation of rate theory. So to explain the equation, so it's HETP is equal to A plus B by mu plus C times mu. So what exactly it is? So C here can be broken into two parts. So one is the C of the stationary phase, and the other C is from the mobile phase. So to give you in detail, HETP is basically the height equivalent to the theoretical plate. So it is the total height that is required for the separation of components, or rather it is the minimum height required for equal distribution of the analyte between the stationary phase and the mobile phase. Then A is the eddy diffusion, or the multi-path effect. I'll tell all this in detail one by one. So I just give you the uh, names, what it is, and then I will explain in detail. Then B here is the longitudinal diffusion, and C is the mass transfer. So mass transfer rate is from two components, that is mass transfer rate from stationary phase and mass transfer rate from mobile phase. And mu that is here is the flow rate of the mobile phase. Now, what is eddy diffusion, or the multipath effect? So as the name suggests, that there will be multiple paths available in the column or plate, due to which peak broadening will occur. Now, why multiple paths will be available? Say, for example, there is an analyte and that is standing in the middle of the column. So it can go zigzag, it can also go straight. So it has many paths. It can choose the shortest path, it can choose the longest path, it can choose a medium path. So anything it can do. So that's why it has multiple paths that it can take. So for example, in a column plate filled with a stationary phase of varying sizes, a single analyte will have different path length due to its different paths that are available to the same molecule because of interparticle spaces. So, where there are bigger particles, there will be a different space. When it goes through smaller or minute particle, then it has a different space. Thus, it will cause peak broadening. Though this does not occur in case of gas chromatography, as gas always tends to choose the shortest path. Now, further, we have longitudinal diffusion. So in longitudinal diffusion, the mobile phase is diffused longitudinally, thereby causing turbulence effect. That is, uh, there would be higher concentration of the solute in the middle when lower concentration, whereas lower concentration at the edge. So in liquid phase, the diffusion uh, the diffusion is less, but in gas phase the diffusion is more. Why? Because the gas takes the shortest route. So, and next is mass transfer. So now mass transfer rate depends upon the affinity between the stationary phase and the analyte. Then it also depends upon affinity between the mobile phase and the analyte, as well as the flow rate of the mobile phase. Low flow rate gives a good resolution, or a low flow rate gives a good separation, whereas when you have a higher flow, it will give you a fast separation, but the resolution will not be very good. So then we move on to the working of the gas chromatography. So gas chromatography, basically, as you can see, is my cursor? Yeah, you can see my cursor, right? So
Yes,
this
sir.
is the gas chamber, and uh, in this, gas is used as a mobile phase, and it is stored in a gas chamber. So this is the gas chamber in which this gas is stored. Now, only gas that are inert in nature or do not react with the sample is used as mobile phase. Why? Because if a gas will react with the sample that you want to isolate, then uh, it will cause a reaction. So you always use a gas that is inert in nature or do not react with the sample. So the example that we use as a mobile phase here is either helium, because it's an inert gas and it does not interact with the sample, or you can also use nitrogen, because nitrogen also does not react with the samples. Next is sample. So sample can either be a gas, a mixture of gas, or liquid. So when the sample is liquid, then that liquid should be converted to gas easily, and if it is getting converted to a gaseous form, then its activity should not change. So only a liquid whose activity upon conversion to gaseous form does not change can be used as sample in gas chromatography, or you can use a gas directly. Then the gaseous mobile phase that is stored here in the chamber is transferred to the injector port. Injector port is where the sample is injected. So it's transferred to the injected port through a gas flow regulator. Now, the role of this gas flow regulator is to control the flow rate, or decide the flow rate of gaseous mobile phase into the sample injector. Now, after the controller is the box that is called as sample injector port. So sample inlet box or sample injector port is always at a higher temperature, and it is at a higher temperature such that the sample that is injected, if it is a liquid, then it is automatically converted into a gaseous phase, or if it is a gas, then mixing of the liquid phase that is coming from here, from the gas chamber, is easily mixed with the sample. Now, then the next is oven or the gas chromatograph. So this is the box that holds the stainless steel gaseous column, and the length of this gaseous column is around 15 to 30 meter long, with solid or liquid stationary phase. Often liquid is used here as stationary phase, but when liquid is used here, then a special thing has to be taken into mind, that liquid should have a higher boiling point. Higher, why? Because this is a oven that is set at a higher temperature. So if the liquid phase is not having a higher boiling point, then it will not be stable. Thus, a stationary phase with a higher boiling point is required. Then, if we talk about examples, so usually we use silicon grease as a stationary phase here in this case. Now, separate the mobile phase mixed with the sample will be injected into the column, and separation will take place. So how the separation takes place here in gas chromatography? Now the sample with low boiling point will move faster, and hence will run through the column first, and it will come out to the detector first. So the first peak that you see here is for the sample with a low boiling point. The lowest boiling point will come faster, and the one with the highest boiling point will come at the last. That is one thing. Now, if there are two components which have similar boiling point or same boiling point, then what will happen is, then the second condition will apply, and then it will be separated based on size. So then the component which will have the smallest size will move out of this column first. So here you will see the peak. So in this chromatography, this first peak is of the molecule which has the lowest boiling point and the smallest size. Then the one with the lowest boiling point but bigger in size will come, and so on. And the last component will be the one with the highest boiling point or bigger size. So that is how it works. And if we talk about this, after the column, the next is the detector. So the detector is the um, thing responsible for detecting the component that is coming out of the column. So often we use mass spec to mass spec is used as a detector. So what mass spec does is it basically supports or helps us to identify the component that is coming out of the column. Now this graph that we have here, so here on this x-axis we have retention time, and on the y-axis we have the intensity. So how intensity basically defines the amount of the component that was present in the mixture, whereas the retention time gives us the idea about the boiling point and the size of the component that we were isolating. So as I said, the component with the lowest boiling point and the lowest size will come first, while the component with higher boiling point and bigger size will come last. So from this detector, we'll get a reference chart of all the retention times of the components that are coming out of the column, and then we cross check it or reference it to a standard retention time chart to identify the molecule that was coming out, identify the component or molecule or gas that was coming out of this gas chromatographic column. Now, there are a few key points, or rather, you can say take home messages of the gas chromatography. So, sample to be separated should be converted into vapor and mix with the gaseous mobile phase. Sorry. Component which are more soluble in stationary phase or bigger in size travel slower. Component more soluble in mobile phase or smaller in size travels faster. Components are separated according to their partition coefficient. Then in gas chromatographic analysis or separation, the sample should be thermostable and volatile. Why thermostable? Because it is often in gas chromatography, the temperature of the oven is also very high. And when the sample is injected, it is converted into the gaseous phase in the injection box, and the temperature of the injection box is also very high. So it should be thermostable and it should be easily convertible into gas without losing its property. Then the number of component in the sample is determined by the number of peaks. So number of peaks that you get in the on the computer determines the number of particle or the number of components that were mixed together to form the mixture. The amount of given component in the sample is determined by the area under the peak. So how much amount was there, that can be calculated by calculating the area of this peak. Then the intensity of the component can be determined by the given the identity of the component can be determined by the given retention time. So the time when it leaves the column is the retention time, and using that retention time, that component is identified using a reference table. Now, one point that I missed out here. So sometimes what happens is when the components with lower boiling point or lower size passes through the column first, and there are still components left in the column with very high boiling point or very bigger in much bigger in size, then for eluting those components, the temperature of this oven is modulated or is changed. It's increased up to 300 degrees centigrade or something, so that the elution of these components with higher boiling point or bigger size is made easier, and this process is called as temperature programming. Now, application of gas chromatography is capable of separating, detecting, and partially characterizing organic compound, particularly when present in small quantities. Then quantitative analysis, that is retention time and volume, are used for the identification and separation. Then for checking the purity of the compound, so if how pure the compound is, for this comparison of chromatography of the sample is done against standard chromatogram of the compound, and this is how the percentage purity of the compound is calculated or identified. Then quantitative analysis, you can do quantitative analysis by measuring the peak area or peak height, and that will give you the amount of your component of interest present in the mixture. Then it is also used for the analysis of drugs and their metabolites. So that was uh, gas chromatography. And if you have any questions, then please.
Hello, sir. Good afternoon, sir.
Yeah.
Sir, my question is that, sir, can you please, sir, show the slide know where the working of gas chromatography, sir?
Yeah.
Like peak, sir.
Yeah, this
Yes,
right.
thank you, sir. Okay, sir. Sir, I have a query in this working. Like, sir, you told the two peak. One is the, sir, lowest peak, and second is the, sir, highest peak.
Yeah.
And whenever showing the lowest peak, that means the boiling. That means the lowest boiling. And whenever showing the, sir, high, that means the high boiling point. So, right, sir? And sir, my question and my query is that, sir, whenever, sir, this peak can't show like this, sir. I mean, sir, artifactors. So what can be, sir? What?
So
if the peak showing the artifactors, then what is the reason behind this, sir? If the showing the artifactor.
So basically in this chromatogram, the first peak that you see is of a component which has the lowest boiling point as well as the lowest size. So the second peak that you see here will be of a component which has a boiling point that is higher than this component, or it will have the same boiling point but will have a higher size.
Okay. Yes, sir.
So further on the third peak, this small peak that you see here, this peak either has boiling point higher than these two peaks, or it will have the same boiling point but will be bigger in size.
Okay,
So,
sir.
so talking about your question on artifacts, if you
Yes,
say
yes, sir. Yes, sir.
artifact, so that artifact could be due to various reasons. I mean, it could be that the say for example there are two components which are same but there is a little bit change in their chemical properties, so the component will come as same. It has a similar boiling point as well as size, so it will fall in the same range, and then you will see overlapping peaks. That's what your question was about.
Yes, yes, sir.
Yeah, so that is of components that are uh, basically, you can say that they are chemically, there is a change in the component but their size and boiling point is the same, so then you will see peak overlap or error.
Okay, yes, sir.
Yeah.
Okay, thank you, sir.
Which is the parameter on the x-axis?
Sorry,
So what is the parameter on the in this chromatogram?
you are asking about the parameter on the axis, if
Yes,
I'm
sir, x-axis.
Yeah, so x-axis has retention time, and on y-axis is the intensity. Intensity basically tells you about how much your component is present in the mixture, whereas the retention time tells you about when that component left the column.
Okay, sir. Okay. Thank you, sir.
So I have a question, sir.
Yeah.
So, like in gel electrophoresis, after separating in different after getting different bands, we use a nitrocellulose membrane to take out the interested band. But in column chromatography, how do we select our uh, region of interest?
Yeah. So basically, in this here, you are getting all the components separated. So gas chromatography you can use for identification. But if you want to separate and use the components that you have separated, you will either have to use high performance liquid chromatography or fast protein, depending upon what kind of component you want to isolate.
Okay, sir.
So
Thank you.
Hello, good afternoon, sir.
yeah.
Sir, I have a question, like a very small query, like why would put a retention gap between the injector and the front of column?
Can you repeat that question, or maybe write because your voice is not very clear?
Sir, now it's clear.
Yeah.
Sir, I was asking like why we put a small retention gap between the injector and in front of the column.
Small gap between the
Injector
injector.
and the column.
So that is the place where mixing of the sample takes place with liquid gaseous phase. So I think you are talking about this place here, right? In the corner.
Yes, sir.
Yeah. So that is the place where the sample gets mixed with the gaseous mobile phase, liquid mobile phase that is coming. Any more doubts?
So, students, if you are working on something, or have you ever used this instrument, if you have any question regarding that, also you can discuss.
Hello, sir.
Yeah.
Sir, I had just a general doubt, sir, that in one of the slides you discussed about various different types of methods of chromatography, sir.
Okay.
So, sir, according to you or according to the results, which one is the most accurate, sir?
It's not about being accurate. I think you're talking about this slide, right?
Yes, sir.
So it's not about being accurate. It's about uh, what component or what sample you have. Depending upon the sample, you choose the type of chromatography for um, purification or identification. Say, for example, if you have antibodies to be purified, then you will have affinity column. If you have, if you want to if you have a mixture of proteins that you want to separate, but it's protein not antibody, then you will use size exclusion chromatography to purify it based on size. Or for example, if you have phytocompounds, normal phytocompounds, you want to isolate, then you will use either thin layer chromatography, or you can also use paper chromatography. So depending upon the use that you have, you can choose what kind of chromatography you want.
Okay, sir. Thank you.
So, I guess there are no more questions. And if you have any question or query, you can, mail us, or you can drop down the message in WhatsApp group. So thank you so much, Dr. Saurabh, you taking out time and you have accepted our invitation. And we always look forward for your support in future workshop. Thank you so much.
Thank you.